Wireshark, you do network forensics, so you should install Wireshark on whatever computer you're using. You could use a virtual machine, but there's no real reason to. It runs fine on every operating system. And so here's one of the files to examine. So download that thing and open it in Wireshark. And this is FTP data. So there it is, coming in Wireshark. And this, by the way, is the recommended way to use Wireshark rather than sniffing live network traffic. It's considered best to examine captured traffic because these handlers for all these different protocols are not very secure. So you see the packets one by one up here, and you can see things like the TCP handshake. Here, the local port 50681 sends, 690 sends a SYN here to 443, and the server sends a SYN-ACK back, and then the client sends an ACK. That SYN-ACK is the TCP handshake. After that, you're ready to communicate with the server on that port. So, going back to my project instructions. All right, so we're going to find an FTP password. So we're just going to, you see there's various protocols here, but we're going to filter for FTP. You can type things in this filter bar, and when it turns green, then you've made something with the correct syntax. So press enter, and now you see FTP data. And now, if you just look at the info column over here, it's easily readable. And you can just see, please log in with user and pass. And here it is, user John and pass flapper, login successful. So you can, this is why FTP is a terrible protocol, unsafe to use. There's no encryption, and it's very easy to see what's going on here. All right, so there's a flag, you find somebody's password here. All right, and then let's try HTTP. HTTP, not HTTPS, suffers just as much from a lack of encryption. So, if I open this one, now I don't see anything because my filter still says FTP. I have to clear that filter, and then I'll see the data here. Now I think for this one, I want to filter for HTTP the same way. All right, and we're going to see an HTTP login, which is not encrypted either, but it's not quite as easy. You can see here it's opening some login page. It's sending post data up to a login page and then getting an answer and doing various posts. So this is a login process happening, but you can't see the password right there. And you can't tell whether it's successful or not easily from right there. So the way to do it is click and expand the hypertext transfer protocol container. So if I click on one of these post logins, I can go down here. This is where you see the layers. This is layer 1, showing you how many bytes went over the wire, which is a wireless transmission in this case, but it could have been wired. This is Ethernet with MAC addresses. This is IP with IP addresses. And this is layer 4 with TCP source and destination port numbers. So those are the lower 4 layers of the OSI model there, and those are the ones that are meaningful. The higher layers pretty much are all blurred into one. And so here, hypertext transfer protocol is, and here you see a form. And if you expand this, it will show you the data. So here's the data, U equals Isaac, P equals password. So that is the username and password that was sent here. All right, so you can see down here what was sent in that post request. It doesn't show it right up there in the summary. Now, you can follow a stream, and you'll see, this is a very handy thing. If you right-click any packet and follow TCP stream, then you'll see the data the way the user saw it without all the addresses and times and stuff. So this is the post request being sent up to the server with username of Isaac and password of Flapper. Here's the server's reply, 200 OK, which means it understood the request. And down here is the response. One thing that's irritating is the response is zipped. Because when you made the request, it said accept encoding gzip deflate. So the requester said it's okay if you zip the reply. And so it is zipped, which is annoying because you can't easily read it here. It makes the network traffic faster, so usually people do let traffic be zipped. But if you're trying to look at the raw package in Wireshark or in Python, it's an annoyance. Anyway, when you follow the TCP stream, it does it by putting a filter up here, TCP stream equals 2. And you can go to different streams this way. Here's the first one, the second one, third one, and so on, and see them. But if you want to get back to the original data, you have to get this back to just plain HTTP. So delete that and put in HTTP and press enter, and you're back to seeing the HTTP here. So if you click the packet and look at the reply, you can now see if it's readable. Wireshark will unzip it. So here's the post, here's the reply. If you look at the raw packet bytes down here, you'll see the reply is unreadable binary junk. But Wireshark will unzip it for you. And now you'll see you entered Isaac and Flapper, login denied. This is the stuff, if you followed the stream, this would be unreadable zipped stuff, but Wireshark will unzip it. And that's why I mentioned Wireshark is insecure. There's a whole library of code submitted by the community that does all this. It recognizes every protocol, it lays it out in this nice friendly way, it decompresses things, and that code is not necessarily secure. There are protocols where that code has flaws. That's why sniffing live network traffic with Wireshark is a risky thing to do. All right, anyway, so we can see now, this is how you can tell what passwords were sent, and you can tell whether it was succeeded. So by looking at this, you can find the password that worked, and then you can try basic authentication. So this is following through history. We had these really old protocols like FTP and Telnet and HTTP that didn't encrypt anything, and then for some reason, at one point, people invented this basic stuff. And here, the way this works is you try to get a page and it tells you you're unauthorized, then your browser will pop up a box and get a username and password and do the request again, and now you'll be approved. Because if you look at this request, you can see it down here. Well, it might be best to just follow the stream. All right, so if you look at this request, it sends a request to go open secretindex.html, and it gets told you're unauthorized. Okay. But if I go to the next request, which I think would be next stream probably, this time you can see the difference. This is a good thing to see. See, it added that one line up there. It added an authorization line, and now I got in. So this authorization line includes the username and password, and as you can probably guess, it's base 64 encoded with the equals at the end. And in fact, all it is username : password converted to base 64. So this is not even encryption, it's just encoding. It doesn't protect your passwords very well at all, but it was considered a step up from the plain text authentication. And again, you could copy this into some kind of base 64 decoder or use Python, or you can just use Wireshark. If you go to here, this is the get that got in, and if you go here, it will show you authorization basic, and if you expand it, it will open it and show you the name and password. So it will undo it. That's what these handlers will do a lot for you. They've written code for every protocol. People have submitted it to pretty much see and everything. So that's basic authentication. Now, this one here is much more challenging, and it's probably most appropriate for students who are taking 123. This is a real red team capture the flag project I did. They call it APT for Advanced Persistent Threat. And what goes on, you analyze this traffic, and it can take a while. You'll find there's an encrypted protocol used here on an unusual port. And then you can read the traffic where the attacker executes Linux command line commands. And you can see where they generate the encryption key and send it over the network unencrypted, and then open an encrypted connection here. So you can get the encryption key, and you can find the tool they used, and you can decrypt it, which is very clumsy in Wireshark. Wireshark, unfortunately, has two places to put in decryption keys, and some versions use one of them, and some versions use the other. So it can be pretty annoying. But if you get it in there, you can actually add a key to Wireshark and decrypt the communications. Then you can also see port knocking, which is a technique where this is a malware's been using this for a while, and some administrators use it. You'll send a TCP request to like port 7000, and it will be denied, saying I'm not listening. 8000, it'll reset, and 9000. And after you knock on the right ports, it will open another port for just a couple of seconds. So this is a way to have a secret way into a machine, which you will never find with a port scan or any attempt to connect. Only when you do the knocks, you have a couple of seconds to connect on another port, like port 22 or something with SSH. And that's what we have here. You'll see an obvious pattern of port numbers where the attacker tried the knocking on many different devices on the network. You'll see it try a series of ports, and then again on another device, and again on another device, and you can find a flag by going through there. And then they finally get in. After they do the 3 knocks, one of the devices is in fact listening for the shell, which means the malware is running on that device, and then they get in with a shell session. They got in more than once, they got in several times, so apparently they've been infecting machines and getting it on there, and then you'll be able to find a flag by getting in there. So there's a lot of extra credit to be gotten here, but you learn a lot about Wireshark doing that stuff. Anyway, that's what I wanted to show you, and I see another question in the chat. Insecure to the sniffer. Yeah, sniffing live traffic is insecure because these handlers here that dissect the protocols, there are hundreds of them, if not thousands. And there are, these are just written by community members and not very well vetted for security. So there are known attacks where you send some obscure network traffic and it causes some kind of vulnerability in Wireshark, like crashing it or perhaps even root code execution. That's why. So in general, if you were to have Wireshark listening as your network monitoring tool, this would be a poor choice for that reason. So what's better is to use TCP dump, which just takes the network traffic and puts it in a file, and then you use Wireshark to analyze the file later. Where's the encryption key stored? Well, in this machine, it's in the preferences. If you go into preferences, some of them have it right here. I'm not seeing it in this one, but the other way to do it is to go in the here, right here, RSA keys. You can put them here, and some versions will use the one you put there, but there's another place to put it too, which is really unprofessional. That's the problem with these tools. Free tools, you know, they're made by a community of like open source people, and they don't have like consistency and logic as much as they should. So now if you go to TLS, here's another place to put RSA keys. And sometimes it looks here and sometimes it looks there. So it's kind of annoying. You'll kind of have to just try them both and see which one works on your system. But when you get the right key in there, it will automatically decrypt whatever traffic it can with that key. All right. I'm going to stop this recording.